Chapter 17, Equilibrium, the extent of chemical reactions. In this chapter, we're going to study the equilibrium state and the equilibrium constant, the reaction quotient and the equilibrium constant, how to express equilibrium with pressure terms, the relation between Kc and Kp, how to compare Q and K to determine reaction direction, and how to solve equilibrium problems. And finally, we'll discuss Le Chatelier principle. Experiments show that most chemical reactions do not go to completion. For example, the key step to synthesize fertilizer is to use nitrogen, hydrogen to make ammonia gas. And so stoichiometry says 1 nitrogen, 3 hydrogen should give you 2 ammonia molecule. So if you add 1 more nitrogen, so initially you add 1 more nitrogen, 3 more hydrogen, and you should get 2 moles ammonia. But instead, in practice, at a certain temperature pressure, not all nitrogen react. Okay, so maybe only 0.1 reacted. So this is reacted. So reacted nitrogen is 0.1 and reacted hydrogen is 0.3. And the ammonium formed is only 0.2. So you only make 0.2, and you still have 0.9 moles of nitrogen left, 2.7 moles of hydrogen left that doesn't react. Okay, and you only get 0.2 moles of ammonia. Okay, and this is determined by nature. No matter how long you wait for the reaction, okay, no matter how long you let the reaction run, you only get a certain amount of ammonia. In this case, 0.2. All right, you still have a lot of nitrogen, hydrogen left, and this is called equilibrium. And this equilibrium can be explained by kinetics. At the beginning, you only have reactants, so nitrogen, hydrogen, and there's no ammonia at the beginning, and so the forward reaction has a high reaction rate. Okay, the reaction rate to go forward is very high because reaction rate is determined by the concentration. So at the beginning you only have reactants, so the forward reaction is fast. With time you start to make ammonia, so the product start to increase, and when you have the product, the reverse reaction, the product also go back to the reactants, and this reaction rate increase. Okay, and this will decrease because the reactants concentration decrease. Eventually, these two reaction rate becomes equal. So forward rate equals to reverse rate at a certain point. All right, you have certain amount of reactants, certain amount of product, and they have equal reaction rate. And this is when the reaction reach equilibrium. Because if they have same reaction rate, then the concentration should not change anymore. Okay, per seconds you make same amount of reactants and same product, so it doesn't change anymore. So chemical equilibrium is a dynamic state because reaction continue to occur, but because they occur at the same rate, no net change is observed on the macroscopic level. This diagram shows how a chemical reaction approaches equilibrium on the macroscopic and the molecular level. The reactant is N2O4 and the product is NO2. Product has a dark brown color. At the beginning, the container contains almost all reactants N2O4, only one product, okay, only one. Now with time, more product is formed. So here you have 3, and you can see the color becomes more brownish. And now, with more time, okay, when we go to C, you can see the container becomes dark brown, and this is because more product is formed. So in this case, you have 1, 2, 3, 4, 5. So 5 product, and you have 9 reactants left. Okay, now if you leave it even longer time, okay, no matter how long you leave it, the reactants product doesn't change anymore. If you count, the product is still 5 and the reactants is still 9, and so it's an equilibrium state where the reactant forward reaction rate equals the reverse reaction rate, and so the the concentration of reactants product doesn't change anymore. Okay, and you can see the color change when the reaction reach equilibrium. In kinetics, we know that reaction rate is determined by concentration. Now we'll talk more about kinetics in the later chapters, but here let's assume the forward reaction is the first order reaction, so the reaction rate should be a constant. Okay, it's called rate constant multiplied by the concentration of the reactants. So in this case is N2O4. Okay, so this is the forward reaction rate, and the reverse reaction should determined by concentration of the product, and so you should have a different rate constant. Okay, this is also constant but different from the forward reaction rate constant times the concentration of the product. Okay, but now you have two of them. Okay, so you can write as NO2 plus NO2. So in this case, the concentration you need to multiply twice. Okay, so that's the reverse reaction rate, which you can also write as N2 squared. Okay, so that's the reverse reaction, and this is the forward reaction. And when the reaction reaches equilibrium, these rates becomes the same. Forward rate equals reverse rate. Okay, now if we divide by K prime on both sides, then you shouldn't change. For example, 2 equals 2. If you divide by 4, then you get 1/2 equals 1/2. So if you have an equation, and if you divide by a certain number in both sides, you shouldn't change the number. So in this case, if you divide by K prime, all right, the equation still holds. But in this case, the right side cancel each other. So now you have K divided by K prime times N2O4 equals NO2 squared. Now, if you divide by N2O4 on both sides, then equation still hold. Now, in this case, the left side N2O4 cancel each other. So here we have this equation. K forward rate, reverse rate constant ratio should equal to NO2 squared, and that's this one, divided by N2O4. Okay. Now note that both of these constants are constant. So this ratio gives you a new constant, and we can define this as a big K, and that's called equilibrium constant. So both small k are rate constant, and that gives you a new constant called equilibrium constant, which equals the product. NO2 is the product concentration divided by N2O4, that's the reactants. So it's the concentration of the product divided by reactants, and that's the equilibrium constant. Now, if the equation has a coefficient, in this case is 2, then you should square it. All right. Similarly, if the reactants has a 2, then you have to square also here. As we have seen from last slide, the equilibrium constant reflects a particular ratio of the product over reactants. So K therefore indicates the extent of the reaction to tell you how far the reaction proceeds toward the product at a given temperature. A small k, according to this equation, small k means P is small and R is large, and that means you only forms a small amount of product. Okay, P is small, so small amount of product is formed. A large amount of reactants that is left, that unreacted. Okay, so it indicates the reaction yield little product before reaction equilibrium. The reaction favors the reactants because you have large amount of reactants that unreacted. Now, a large K constant, on the other hand, tells you this P is large, the product concentration is large. That means you forms a lot of product, and the reactance is small. That means most reactants already reacted, only small reactants concentration left. Okay, so it indicates reaction reaches equilibrium with very little reactant remaining, and the reaction favors product. It forms a lot of product. So big K, more product favors product. Small K, small product, more reactants left, so favors reactant. This diagram shows 3 different reactions with different K constant. For example, the first reaction is nitrogen oxygen forms nitrogen oxide with a K constant 10 to the minus 30. 10 to the minus 30 is a very small number. Okay, minus 30 power means 0.000, okay, altogether 30 zeros and then 1, and that's a very, very small number. Okay, so remember K is product divided by reactant. Okay, the concentration product divided by reactants. So if you have a very small K, that means P product is small. So if you look at the diagram, the reactants is represented by blue dots and the product is red. And here you only have one red and mostly are blue. Okay, so a small amount of red divided by large amount of blue, and that gives you a small K constant. So the reaction favors reactants. Okay, favors reactants because you have so many reactants left, only very small amount of product. Okay, let's look at another reaction. CO oxygen forms CO2, and this has a very large K constant, 10 to the 22nd power. And so 10 to the 22nd power means 0, 0, 0, 0. So you have 22 zeros. That's a huge number. Okay, and again, it's K is the product divided by reactants. So if this is a so large number, that means you have a lot of P product, small amount of reactants. So here, if you look at the diagram, red is the reactants. So you only have one reactants, majority are product. Okay, so product divided by reactants give you a large K. Okay, so in this case, large K favors product. Okay, because mostly are product. Now for bromine chloride, so that's reactants forms bromine and chlorine gas, and this gives you a intermediate K constant 5. All right, so again, reactant product divided by reactants. If we have a moderate K, that means reactants product are comparable. So if you look at this diagram, you have a similar amount of reactants and the product. So again, this diagram shows you the equilibrium constant measures reaction extent. All right, large K. Okay, large K means more product. Small K means more reactants. We have seen from last few slides that most chemical reactions are reversible, and they will eventually reach equilibrium. And the equilibrium constant is the ratio of the product concentration over the reactants concentration. So for a general reaction such as this one, A plus B goes to C and D. A has a coefficient A, B, C, D. The equilibrium constant should be the concentration of C of the product raised to the power, okay, coefficient, and the product D the power, and A reactants concentration, okay, and the reactants B concentration raised to power B. Note that this is equilibrium, and so the reaction already reached equilibrium. So the concentration are all equilibrium concentration. So usually we'll have a label here EQ for each equilibrium concentration. So that indicates this concentration are equilibrium concentration of the product and the reactants. And this ratio will be equilibrium constant. So it's a constant determined by nature. Now, what if the reaction has not reached equilibrium yet? We can still use the ratio of the product, okay, product C and D over reactants, but these are not equilibrium concentration yet. And so this ratio shouldn't be a constant. And this is called a reaction quotient. So at any time, you can write a ratio of the product over reactants, but this is not a constant, and this is called the reaction quotient. Reaction quotient gives you the ratio of product concentration to the reactants concentration at any point. But the equilibrium constant is a constant that is only when the reaction reaches equilibrium. This ratio will be equilibrium constant. So Q is arbitrary at any point. But when the reaction reaches equilibrium, then this ratio Q equals K. For a particular system and a temperature, the same equilibrium state is attained regardless of the starting concentration. So no matter what concentration you start with, eventually the reaction reaches equilibrium, and the ratio of product over reactants give you K. It doesn't change whether whatever the reactants concentration you start with. Eventually you get the same ratio of product over reactants when the reaction reaches equilibrium. But the value of Q can change. You can calculate Q at any time, the product over reactants. So Q can be any value, all right? Any time you can calculate the Q, all right? But the Q indicates how close the reaction is to the equilibrium. For example, if you calculate the Q, which equals K, that means the reaction already reached equilibrium. But if Q is very different from K, okay, very different from K, that means the reaction is far from equilibrium. Okay, from the value of Q and K, we can predict whether the reaction go forward or go reverse. Okay, we'll see in the next few slides. This diagram shows the concentration, reaction quotient as a function of time for the reaction that go from N2O4 to NO2. So at the beginning, you have a high concentration of N2O4, 0 NO2, so no product, only reactants. Okay. Now, if you calculate reaction quotient, the product is 0. Okay, no product, and divide by reactants, so N2O4. So you have certain concentration, which is 0. So at the beginning, Q is 0. Now, at a certain time, here you see the concentration of product increase, and the reactants decrease because the reactants is consumed, and so the Q now is concentration of product divided by concentration of reactants. So with time, product increase, reactant decrease, so Q increase. So for example, here at the beginning 0, and then you get let's say 90 here. Okay, Q becomes 90. So increase time, product increase, reactant decrease. So 90 becomes 100. Eventually, now here becomes let's say 120. Okay, so then with time, you can see it doesn't change anymore. So the Q remains 120, and that's the equilibrium constant. So in other words, reaction reach equilibrium, and the reaction quotient equals K, which is 120. Okay, so a small q, okay, a small q means you have lots of reactants, you have no product. Okay, and increased q means reaction go forward, approach equilibrium constant, and eventually it becomes K. Okay, Q becomes K. Now, is that possible Q is greater than K? Okay, this example shows we start with Q equals 0, and then increase until Q becomes K. So it's always less than K. But is that possible Q be greater than K? Well, it is possible if we start with the product. So in this case, the reactance is N2O4. The product is NO2. Okay, so if you start with N2O4, then the Q is always smaller than K until it becomes the same as K. But on the other hand, if we start with NO2, then initially you have lots of product, you have no reactants, so you have a very large Q. So Q can be K, but the reaction K is a constant that determined by nature. So if Q is greater than K, that means the reaction has to go reverse so that it will consume product and it will form reactants so that the Q will decrease and eventually becomes K again so that it reaches equilibrium. So if Q is greater than K, that indicates the reaction has too much product and it will go reverse reaction and eventually becomes equilibrium. This table again compares reaction quotient and equilibrium constant for the same reaction N2O4 and O2. The reactance is N2O4, the product is NO2. Okay, so we have 4 experiments with different initial concentration. In experiment 1, we start with 0.1 reactants, 0 product. Okay, so if you calculate the Q, you should use product divided by reactants, 0 divided by 0.1. That gives you 0, right? So that's similar to the last slide's diagram at the beginning. We have no product, so Q is 0. Now with time, more product is formed, Q increase. So 0, then increase, okay? And then when you increase Q, you increase product, eventually becomes equilibrium. So at equilibrium, reactants product 0.193 is formed. Reactants 0.0357 is left. And if you use product divided by reactants, in this case 0.193, don't forget raised to the second power. So you have a coefficient here, and then divide by 0.0357, and that gives you 10.4, and that's the equilibrium constant. Okay, so Q becomes K when the reaction reaches equilibrium. In second experiment, we start with the product, no reactants. Okay, so how do you calculate the Q? Q is product divided by reactants, so it should be 0.1 square divided by reactants. Note that anything divided by 0 is infinity. Okay, so you have a very large Q, okay, as we discussed in the last slides. A very large Q indicates too much product. In this case, is infinity, so we only have product, no reactants. Now note that for any reaction, if you let the reaction proceed, eventually it should become equilibrium. So if we have too much Q, Q is too large, greater than K, then Q must decrease. Okay, must decrease so that eventually becomes K. This is determined by nature. Q reaction must reach equilibrium constant. So if Q is greater than K, it must decrease it. How do you decrease Q? It go reverse reaction. So go reverse reaction so that it will consume product and increase reactance, that will decrease Q. Okay, so at the equilibrium, we can see the product from 0.1 becomes 0.0982, and the reactance increased to 0.00924. And you use product divided by reactance. Also, don't forget the square. Okay, and that give you 10.4. Okay, again, you can see the equilibrium constant is the same, even though we start from different reactants and product concentration. The Q are different from 0 to infinity, but K is the same. When the reaction reaches equilibrium, the ratio of product over reactants is the same. We can also mix the same amount of reactants and the product. You get Q 0.05. When the reaction reaches equilibrium, the ratio again 10.4. Okay, so if you look at all these 4 experiments, you start with different reactants product. You have different Q. Okay, Q can be any value. Okay, because you can mix different reactants of product and the reactants concentration. So you get different Q, but the K is the same. So when the reaction reaches equilibrium, the ratio must be the same. It's determined by nature. When calculating equilibrium constant K or reaction quotient Q, we use the concentration of product divided by the concentration of reactants. Sometimes it's not that straightforward. For example, for a heterogeneous reaction such as this one, calcium carbonate forms calcium oxide and CO2. The reactants is a solid, product has a solid and a gas phase. And this is called a heterogeneous reaction. Reactants product has different phases. A pure solid, such as these two, or liquids, always has the same concentration because they have same number of moles per liter or of solid or liquid, so they don't change. The expression for Q and K include only species whose concentration change as the reaction approach equilibrium. So because pure solid and liquid concentration do not change, so they are omitted from expression for Q and K. And so usually in this case, Q should equals to concentration of let's say calcium oxide, CO2 divided by reactants CaCO3. Okay, but because this is a solid, we shouldn't include in the expression only CO2. All right, so in this case, the Q is only CO2 because it's a gas phase. This diagram shows the equilibrium constant for the same reaction we described in the last slide. So calcium carbonate decompose into calcium oxide and the gas phase CO2. Okay, solid, solid, and the gas phase CO2. Okay, so the equilibrium constant, so the reaction quotient is only determined by CO2. Similarly, equilibrium constant is determined by CO2 when reaction reach equilibrium. Okay, so if you look at the two diagrams, you can see we have different amount of calcium carbonate, different amount of calcium oxide, but the CO2 are the same. So if you count, the left side has 8 molecules CO2. The right side also have 8. When the reaction reach equilibrium, they give you same amount of calcium carbonate or calcium carbon dioxide, okay, gas phase, and the pressure is the same, okay, because the reaction only determined by the gas phase CO2. The solid doesn't count for the equilibrium constant. Now let's look at the sample question 17.1. In this question, you're asked to write reaction quotient Q for the following reactions. Okay, to write the reaction quotient, first step, you need to have a balanced reaction. Okay, so the first one, you need to balance it. Okay, and you have 2 N2O5 forms 4 molecules NO2 plus oxygen. Okay, now we can write reaction quotient. But note, this reaction is a homogeneous reaction because all the reactants and products are the gas phase. They are in the same phase. So when you write reaction quotient, you use the product divided by reactants. Okay, but don't forget, when you have a coefficient, you should raise to the power. So the product NO2 raised to 4th power times oxygen divided by reactants N2O5 to the 2nd power, because you have a 2 here. All right, so balance the reaction, and if it's a homogeneous reaction or a gas phase, then you just include all of them. Okay, don't forget the coefficient. Okay, let's look at the second reaction. Again, balance the reaction. Okay, so this is the balanced second reaction. Okay, and now because all of them are gas phase, so they are all included in the Q. So product divided by reactants. So product CO2 to the 3rd power, okay, here 3rd power, and water to the 4th power, and C3H8 times oxygen to the 5th power. Okay, next, okay, we need to balance the reaction, and notice that this reaction is a heterogeneous reaction. You have solid, pure solid, liquid, aqueous solution, and the gas phase. Okay, note that pure solid, pure liquid, their concentration do not change, so they shouldn't be included in the Q. Okay, reaction quotient or equilibrium constant. So don't include pure solid, pure liquid. Only include gas phase and aqueous solution, because aqueous solution concentration also change. And so in this case, the equilibrium constant is the product divided by reactants. So these are the reactants shouldn't be included, only product. And in this case, you have a 2 here, sodium hydroxide, so raised power 2 times hydrogen gas concentration. Suppose we have a reaction that includes several steps. Okay, for example, A first forms B, and then B forms C. Okay, so the overall reaction should be A forms C, because you start with A, you end up with C, so A goes to C. All right, now in the first reaction, B is a product. In the second reaction, B is a reactant. Okay, so you forms B in the first step, you consumes B in the second step. So you can simply add these two reactions but cancel B, because it formed and consumed. All right, so in the overall reaction, it does not appear in the overall reaction, just A goes to C. Now for this kind of overall reaction, the reaction quotient should be the multiplication of the individual reaction quotient. For example, Q1, all right, for the first reaction should be product B divided by A. In the second reaction, reaction quotient should be, let me write here, should be product, in this case is C divided by B. Okay, so B is the reactants, C is the product. If you multiply Q1 times Q2, okay, then you can see B as an intermediate cancel each other. One is the reactants, one serves as a product, so they cancel each other, and that gives you C divided by A. And this is exactly the product for the overall reaction divided by reactance of the overall reaction, and that is the Q for the overall reaction. So overall reaction is the reaction quotient is a product of the individual reaction quotient. Similarly, the overall reaction equilibrium constant is the product of the individual equilibrium constant. Now, for a reaction A goes to B again, the reaction quotient is B divided by A. Now B also forms A, that's the reverse reaction. So if this is a forward reaction, this is a reverse reaction. So for forward reaction is B divided by A. For reverse reaction, then it's reverse reaction A is the product, so it's A divided by B. And then you can see Q reverse reaction, this one is 1 divided by forward reaction quotient. Similarly, equilibrium constant for the reverse reaction is 1 divided by forward reaction equilibrium constant. Now, for a chemical reaction, again, let's use A forms 2B, for example. For this reaction, the reaction quotient is B squared to A. Okay. Now, we can multiply by a common number on both sides. For example, we can write 2A forms 4B. Okay. The reaction is still balanced. And in this case, then Q prime will be B to the 4th power, A to the 2nd power, or B to the 2nd power over A, and then to the 2nd power. Okay, and this inside the parenthesis is the Q, original Q. So if this is Q1 for this reaction, and this is Q prime for after you multiply a common number, then the Q prime is Q, original Q, to the 2nd power, which is the number you multiply on both sides, the common number. So in general, if you multiply n, then the new Q should be the initial Q or original Q to the nth power. So similarly, the equilibrium constant is after you multiply a common number should be the original K raised to the power of n, which is the number you multiply by both sides on the reaction. Now let's look at simple question 17.2. A chemist wants to find equilibrium constant Kc for the following reaction. So for this reaction, we want to find the Kc. And there are 2 known reactions are given. And these known reactions has given equilibrium constant. So we want to use these 2 reactions to find out a unknown reaction. Okay, so this kind of reaction, we must manipulate the known reaction 1 and 2 so that we can add them together to give you the target reaction. Because if we can do that from last slide, then the equilibrium constant for the new reaction will be the product of individual reactions. Okay, now let's compare the known reaction and unknown reaction. So for the unknown reaction, ammonia is a reactant, but in the first reaction, ammonia is a product. Also, nitrogen is a reactant, but unknown reaction, nitrogen is a product. So we must reverse the reaction 1 to get the unknown reaction. So that indication that we have to reverse this reaction. And from last slide, if we reverse a reaction, the equilibrium constant will be inverse. So 1 divided by the initial or original K constant. Okay, so that's one you need to remember. Now, if we look at the second reaction, hydrogen gas, iodine here, in the unknown reaction, you have 3 iodine. Here you only have 1. Okay, similarly, you have 2 hydrogen iodide, but unknown reaction you have 6. So that indicates that you need to times 3 of this second reaction in both sides, and that give you iodine and hydrogen iodide. Okay, so if we multiply a number 3, okay, then the new equilibrium constant should be the original constant raised to the power 3. Okay, remember in the last slide, you raise to nth power if you multiply a common number n. Okay, so here's how we do it. Okay, first we reverse the first reaction. Okay, and so ammonia from product becomes reactants. Nitrogen from reactants becomes product. Hydrogen becomes product. And for this new reaction, the equilibrium constant will be the 1 divided by the original K. Okay, so 1 divided by 0.343. Okay, that gives you 2.92 for this reaction, for the reversed reaction. Second, remember, this one we need to multiply a common number 3 on both sides. Okay, and by doing that, the new equilibrium constant you need to raise to the 3rd power of this one. Okay, 54, and that gives you 1.6 times 10 to the 5th power for the new reaction. Okay, now we can add these 2 reactions. Okay, when you add these 2 reactions, you will see hydrogen is a product in the first reaction, but reactants in the second reaction. So it cancels each other, and that gives you the reaction that is the unknown reaction. Okay, so the unknown reaction is obtained by adding new reaction 1 and 2. And according to the previous slides, we know the equilibrium constant for this overall reaction is the product of the individual K. Okay, so here shows you how we get it. So we already have the conclusion. K should be the product of the individual K, which is this 2. So 2.92 times 1.6 times 10 to the 5th power. And that gives you 4.7 times 10 to the 5th power. So to do this question, we need to know that if we reverse a reaction, the equilibrium or reaction quotient should be 1 divided by original reaction quotient. Same for equilibrium constant. And if we multiply a common number on both sides of a reaction, the new reaction quotient or equilibrium constant is the original one raised to nth power. And if we add the several reactions together to give you overall reaction, then the equilibrium constant of overall reaction is the product of the individual K. Okay, and you have to compare reactants and the product and see if you need to multiply a common number or you need to reverse the number to get the unknown reaction. Let's summarize Q and K. For a reaction A goes to B, the reaction quotient is the product B divided by A. And the reaction equilibrium constant is also the ratio of B divided by A, but the concentration must be equilibrium concentration. So Q is arbitrary at any instant, but K is only when the reaction reaches equilibrium. For B goes to A, the forward reaction quotient is product A divided by B. Okay, so this is the product divided by reactants B. Now the reverse reaction will be B divided by A. So the relation for forward and the reverse reaction quotient is inverse. Similarly, the equilibrium constant between the forward and the reverse is also inverse. Now, if a reaction is a sum of several steps, okay, for example, here A goes to C and then C goes to B, the overall reaction is A goes to B, okay, because you start with A, you end up with B, and C is the intermediate. They cancel each other. So in this case, the overall reaction, so for this one, the reaction quotient should be the product of individual Q. So Q1, Q2. The product of them give you the overall reaction quotient. Similarly, the equilibrium constant for the overall reaction is the product of individual K constant. If a reaction equation is multiplied by a common number n on both sides, then the new reaction quotient is the original quotient raised to the power of n. Okay, same thing is for equilibrium constant. Now, if a reaction involves pure solid or pure liquid, we should omit solid liquid in the reaction quotient and equilibrium constant. So we only include gas phase or aqueous solution in the equilibrium constant or reaction quotient. So far, we have learned how to express QC and Kc. C represents concentration. Concentration is moles per liter, okay, moles, number of moles per volume. So, for example, in this reaction, the Kc is expressed by the product NO2. So NO2 raised to second power, here you have a 2, divided by reactant NO second power, so here second power divided by oxygen. Note that if it's Kc, that means equilibrium constant, so these concentrations are equilibrium. Okay, EQ means equilibrium concentration. Now, if they are not equilibrium concentration, then this ratio should be QC, okay, reaction quotient. Now, because the reaction involves gas phase, all are gas phase, so we can express the equilibrium constant in terms of partial pressure. Okay, again, we can write as product, okay, divided by reactants. Again, second power for NO2, second power for NO, first order for oxygen. So the format are the same for Kc, Kp, but one is for concentration. Okay, the bracket means it's concentration. Here, P is the partial pressure. So this one, Kp means the equilibrium constant in terms of partial pressure. Now, we learned that for ideal gas, the pressure, volume, temperature, number of moles, they are related by equation called ideal gas law, PV equals nRT. Here, the N is number of moles, R is a gas constant. If everything is SI unit, then R has a value 8.314. Okay, now if we combine these three equations, okay, 1, 2, 3 equations together, we can derive equation to relate Kc and Kp. And this equation is Kp, okay, which is the equilibrium constant in terms of partial pressure, equals Kc, which is the equilibrium constant in terms of concentration. So this is this one, and this is this one. Usually they are not the same. You need to multiply Kc by RT to the delta nth power. R is the gas constant, temperature, delta n is the number of moles difference between reactants and the products in gas phase. So again, let's look at this equation. In the reactants, you have 2 moles NO, 1 mole oxygen. So the total number of moles in reactants is 3. And the product is 2 moles NO2. So it's 2. And therefore, delta N in this case should be the product 2 minus reactants is 2 plus 1. Okay, so 2 is NO1 is oxygen. That's so add together is 3. So 2 minus 3 is negative 1. Okay, so in this reaction, delta N is negative 1, and therefore Kp. Okay, if you write equilibrium constant in terms of partial pressure, this will be Kc, equilibrium constant in terms of concentration, but you need to times RT to the negative 1 power, or Kc divided by RT. Okay, so that's for this special case. All right, now if a equation delta N is 0, that means the number of moles gas phase in the reactants is the same as in the product, then Kp equals Kc. Let's look at sample problem 17.3. So in this question, we have equilibrium constant in terms of partial pressure, so Kp for this reaction. And we want to find out equilibrium constant in terms of concentration, Kc. So to do this kind of question between Kc, Kp, immediately you should remember the equation Kp equals Kc times RT delta N. So in this case, we know Kp. We want to find the Kc. Okay. Now because Kp equals Kc times this one, so Kc should equals to Kp divided by RT to the delta nth power. Okay. Now Kp is given here. R is the gas constant. Now T is the temperature, and here given is 218 Celsius. Now in this equation, you must change to Kelvin. Okay, so first you need to change T to Kelvin. And what is delta N? Now delta N is the number of moles between reactants, the product for gas phase. So for this reaction, the reactants is solid. There's no gas phase, so it's 0. For product is ammonia and hydrogen sulfide, so it's 2. 1 plus 1 is 2. So delta N equals 2 minus 0, product minus reactants, and that gives you 2. Okay, so you have delta N. Now what about gas constant R? Now if everything is SI unit, it should be 8.314. But if the pressure is atmosphere, as we usually do, then the R constant is 0.0821 liter atmosphere per mole per Kelvin. So R constant depends on the units. And if the pressure is atmosphere, and you should use this number. Okay, so now we first calculate delta N. We convert temperature from Celsius to Kelvin. So to do that, you add 273.15 to give Kelvin. So this will be the Kelvin. Okay. And so now the Kc should be Kp divided by RT to the delta N, which is the second power. And that gives you 1.2 times 10 to the minus 4. As we already mentioned, the reaction quotient Q indicates the direction in which a reaction must proceed to reach equilibrium. For example, A goes to B. So you have Q equals product divided by reactants at any instant. And the equilibrium constant is the product at equilibrium divided by reactants at equilibrium. So if Q is less than K, remember reaction eventually must reach equilibrium. So no matter what concentration you start with, eventually Q must equal to K. Okay, that's determined by nature. So if Q initially less than K, then B must increase, A must decrease, so that eventually Q increase and becomes K. Okay, so that means you must increase the product and decrease the reactants. Okay, so decrease reactants, increase product. In other words, the reaction go forward. Okay, so we know if Q is less than K, reaction go forward to increase product and decrease reactants. On the other hand, if Q is greater than K already, so if this is already greater than K, the reaction must proceed so that eventually it equals K. So how to do that? It must decrease B and increase A. Decrease the product, increase the reactants. To do that, it must go reverse. Okay, if the reaction go reverse, it will decrease the B, which is the product, and increase reactants. So the reaction go reverse. Now, if Q is already equal to K, that means the reaction already in equilibrium, so no further net change take place. This diagram again shows the relationship between Q and K. When Q equals K, the reaction already at equilibrium, no net change. Okay. Now, when Q is less than K, note that no matter what Q is, K is the same. Equilibrium constant does not change, but Q can change. So if Q is less than K, reaction must proceed because by nature, eventually Q has to equal to K. To do that, it has to increase K. To increase K, it must increase product because Q is a product divided by reactants. So to increase K or Q, it must increase product, and that's the forward reaction. Okay. Now, if Q is already larger than K, all right, again, the reaction has to proceed so that it will equal to K eventually. Okay, so go this direction so that you decrease Q. How do you decrease Q? You must decrease product, increase reactants, and that's the reverse reaction. So reaction go reverse. Simple problem 17.4. For the reaction A goes to B, B also go back to A, the equilibrium mixture at 175 degrees is this two, okay, A and B concentration. Note that these are equilibrium concentration. So A equilibrium is 2.8 times 10 to the minus 4, and B equilibrium. So with these two, we can immediately calculate equilibrium constant. Okay, equilibrium constant here is the concentration equals product equilibrium divided by reactant equilibrium. So this information allows us to calculate equilibrium constant for this reaction. And the question is, in each scene, does the reaction go forward or reverse? Okay, from previous slides, we know that to predict the direction, we need to know Q in each scene. So Q1, Q2, Q3, Q4, and compare Q and K. If Q is less than K, the reaction go forward. If it's greater than K, it go reverse. If Q equals K, reaction is at equilibrium. And so that's our plan. So here's our solution. First, we calculate equilibrium constant, which is the equilibrium concentration of product divided by reactants, which is given in this question, and that gives you 0.43. And now we calculate the Q in each scene. So, for example, in 1, the product is blue dots, so you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 blue, that's the product, and the red 2, so that's the reactants. So 8 divided by 2 give you 4. So in scene 1, QC is 4. In scene 2, the product blue has 3. Okay, 1, 2, 3. And the reactants has 7 red dots. So you have 3 divided by 7, and that gives 0.43. Similarly, you can calculate QC for scene 3, which is 0.67, and for 4 is 0.25. And now compare Q and K. We can predict the direction. Okay, for example, in scene 1, because QC is greater than KC, so Q is greater than K, and therefore you have too much product. The reaction go reverse to decrease Q, to decrease product increase A. So reaction go reverse, in other words, go to the left side. Okay, because the reaction go from A to B, that's the forward, and B to A is reversed. So you go to the left side means it's a reverse reaction. Similarly, in scene 2, QC is exactly same as KC. So the reaction at equilibrium, no net change. Number 3, QC is 0.67, again greater than 0.43. So similar to number 1, reaction proceed to the left side, reverse reaction. The last one is 0.25, which is smaller. So if Q is small, that means the reaction must proceed forward, go right side, so that it will increase product and increase Q, eventually becomes K. Simple problem 17.5. This question is similar to the last question, except instead of using molecular scene, we use concentration to calculate Q and then determine the direction. So we already have Kc. So Kc is given 0.21, and at a point during the reaction, concentration of reactant and product are given. Okay, so the question is the reaction at equilibrium? If not, which direction it goes? Okay, so again, to predict the direction, we need to know the Q. Okay, we calculate Q by the given concentration here, 2 concentration. So first, we calculate Q, which is the product NO2 raised to the 2nd power, okay, because you have 2 here, and divide by reactants, and that gives you 2.5. So at this point, you have reaction quotient 2.5, which is greater than Kc, because Kc is 0.21, so it's greater than Kc. If Q is greater than K, that means the reaction has too much product. It must decrease product, increase reactants, and that go to reverse reaction. Okay, so the answer is the reaction is not at equilibrium and will proceed from right to left. Okay, reverse reaction is to the left side, proceeds to the reactants. Please read your textbook, chapter 17, until sample problem 17.5. For 8th edition, it's page 760. And go over my lecture video if necessary, and practice on the follow-up problems. If you have a question, email to me, or let's set up an online conference meeting.